Assalamu alaikum warahmatullahi wabarakatuh. We are going to start the new chapter, chapter 7, and that's the numerical solution of ordinary differential equations. Very important part of our discussion. And we are going to distinguish it from the last part we have discussing till now, last 6 chapters. In all this chapter, we are discussing the analytical solution. And here we are going to discuss the numerical solution. The numerical solution is the function of y, which is the solution is defined in a certain interval, each point of the interval. And here in the numerical solution, we define the interval, but on the points on the interval, the solution is being defined. So there are some equations we say we can solve it as we have been discussing different type of differential equations. And this especially when we have the first order differential equation, then second order differential equation with variable coefficient, with the constant coefficient. Then we have the equations with the homogeneous, non-homogeneous. Then in the coefficients, we have seen that sometimes it's not possible to solve it very easily. We got a particular type of differential equation, the Cauchy-Euler equation. We said we can find the analytical solution for that one. Then after that, we just introduced the series solution. And with the help of series, we can just solve our differential equation. So that was but there is the end of that one. So when sometime we have the differential equation where we don't have any method to solve it. So there we can have the numerical methods to solve our differential equation. Very interesting, very easy, and now the technology is there. But we are going to understand how the method is working. Otherwise, you have the softwares, MATLAB or this, you can use immediately the formulas or the subroutines, the programs to write your solution. You can do it. But here in this course, at this point, we are trying to understand how the method is working, what is the background of the method from the mathematics. So application is not difficult. Application, you can do it very easily. But we try to understand the method. When you understand the method, how the method is working, then you are able to improve that one. You are able to modify that one. And if you are having a problem in your solution, then if you know how the method is working, or the detailed method, then you can modify your method also. So that's the idea why we are going to take this one, the solution for this one. First, here we are going to discuss the numerical solution for the ordinary differential equation. We are not discussing the partial differential equation. But anyhow, inshallah, I will be continuing with these courses and I will give you the numerical method of solving the partial differential equation. But at the moment, we are using this one. And then I can just tell you one thing, that the key for all this method is the Taylor series. We have studied Taylor series in our calculus 1 or calculus 2, but there we don't know that how much application this has. They have many applications. I say this is the foundation of the numerical methods. So we have in physical situation. When we narrate the physical situation, we get the mathematical model. From the mathematical model, we translate this mathematical model that get the differential equation and all that into the model. We say numerical model. Numerical model is that we can just give it, and we can use this method to solve it through the computer, through the programming. That's the numerical method. But there is a difference between the solution of that one, the solution of this mathematical model, mathematical equations. Mathematical one might mean, for example, the differential equation is the differential equation, and it contains the initial values, or it contains the boundary values, is initial value problem, or boundary value problem, or initial boundary value problem. So this, and then we get the solution, and that solution is an analytical solution, or sometimes say this is the exact solution. But here, when we use it numerically, then we say this solution is a numerical solution. This is an approximate solution. It's not the exact solution. There is a difference between this numerical solution and when we find the data and we say at the point we find the analytical solution, also numerical solution. We make the comparison. When we make the comparison, we find there is a small error in that. They are not equal. They are not same. This is the error in method. And this error must be not propagate in the method. If it's propagating in the method, in the calculation, then the calculation become unstable. And we say the method is not accurate. The accuracy is being suffered. Moreover, we try to find, because we having now, when you use the Taylor series, you get to have y dash, y double dash, y triple dash, y2. But there is a limit how much derivative you have to find. And then depending upon the function also, how much time you can differentiate that one. So that becomes laborious. So we just say we take only one derivative or two derivatives, second order derivative. We limit over them. We leave all other part of that one. So that part which you're going to leaving, that's creating error in the method. So because numerically we are not taking that part here, but it's having some impact on that one. We say here that our When we solve numerically, then we take the value delta x. Delta x, we say h, or we say the mesh size, or we say the distance between 2 points. We say that must be very near to 0, very, very small. When it's very, very small, when we take the power of that one, they become much smaller. So in this way, we say there the values, the impact of that one is very, very, very small. So we neglect it, we are not getting, we may get the solution, the numerical solution and the analytical solution may be the same, coinciding. When you take 3 decimal places or 4 decimal places, or 5 decimal places, that depends how much decimal place we are taking. Mostly we take 2 or 3 decimal places. Then we can achieve the accuracy, high accuracy, by 2 or 3 decimal places. Then on that basis, when we make the comparison, then we are having different way to improve our method. We are going to discuss that one. Then we have the class of method. We say here single point method, 1 point method, and multi-point method. In 1 point method is we take 1 point and we find the solution the second point depending upon this 1 point. So in this way we are only 1 point is involved when we are going to discuss the solution. The same 1 point method. This is Taylor series method. We discussed Euler method, also is 1 point method. Then we have the Runge-Kutta method, it's also 1 point method. But then we are having the methods which are taking more than 1 point. Maybe 3 points they are going to take. So we want to calculate this value but need this point and this point also, 2 points. So here, when we have more than 1 point, it means we need some value before. So make some calculation to get the result and then we apply the result. So these methods are, say, multi-point methods. Also we say these methods as predictor-corrector method. They predict the value and we correct the value. So it's very interesting, and we are able to make the achievement that our by the numerical methods we are going to converge to the exact solution, very near to this. Very small error is there. So that's why we can apply this numerical method and this make life very easier, and we can have very big projects on that when we can apply our numerical methods to find the solution. It's being applied, and we can make a lot of experiment which we can't do in nature, but we can do with the help of numerical methods a lot of experiments because it's easy. The speed of the computer that decreases the time for calculation of the big models. Yeah, we are just taking very small part of that one to make the understanding what the numerical methods are for ordinary differential equation. But here in nature, when you say, for example, there is a model which contains whole C, whole C, they are being modeled, and then after that they are decreased. The mesh size is being decreased with the power of the computers, and we can model the whole sea for that one. We can have the aeroplane, we have the model for that one, ships, harbors, we have the mechanical systems, we are having the model for that one. We just discuss the stresses on that and all that. So that's very interesting part of the knowledge which is being applied nowadays for reproducing the nature, reproducing the prototypes of things, and just make the calculation of different impacts of different things, different forces on different constructions or different things we are going to invent. So that's the things which we are going to use by using the numerical method. But again, I'm saying we are trying to understand what the numerical methods are.